All right, hello. Welcome to Lab 2, the magnetic field of a bar magnet. So let's get started. All right, so the introduction to Lab 2. The purpose of this lab is to measure the distance dependent of a magnetic field due to a small bar magnet. And in this lab, we'll use the Biot-Savart law to compare experimental measurements to the distance dependent predicted by the equations for the on and off axis magnetic fields. So to dive into the results that were found by the experimentation, we found N to be negative 2.8134, which is also relevant to the slope. And then the magnetic dipole moment was found to be 6.75 amp meters squared. So the physical principles used in this lab, first was the magnetic field of a dipole, which is a closed circulation of an electric current. And that is, you can see that here in the formula below. Next was the Biot-Savart law, which relates magnetic field to a small current. And again, that's shown by the formula there. And then lastly was the distance dependence formula, which is the magnitude or represents the magnitude of the magnetic field due to a bar magnet, and it falls off with this saying that it falls off to a distance. And you can see that in the formula below. And then going back to the magnetic field of a dipole, basically what it says is the inside magnet is there are several electrons circulating around an atomic nuclear, and they're spinning on the axis. And what this does is it creates a dipole of magnetic field strength. So here's our on-axis data. On the left is the distance, is various distances, distance measurements for magnetic field strengths. And then on the right is a linearized plots of these averages shown on the left table. Here are our calculations. And so we utilizing the fundamental principles that we discussed earlier, we could find the measurements here at the bottom. And so first took from our table the slope, which is n, of negative 2.8134, and we were able to calculate that to find k by doing the inverse log, which was 1.35 times 10 to negative 6. And then using our formula from earlier, we found nu to be 6.75 amp meters squared. Here's our off-axis data. To find the off-axis data, it's the similar procedure as the on-axis data. However, and what we do is we move the magnetometer up and perpendicular to the direction of the axis. And so in this table here are the results of the X, Y, and Z components at perpendicular distances. And that's what's found in the table. And as you can see the difference from the on-axis data to the off-axis data here in the pictures below in the movement of the magnetometer. Here's a computational model using GlowScript. On the left, basically what we did was created a function for the magnetic field, and we used the initial conditions from the magnitude found. And so it's not listed here, but from the magnitude we found earlier, that was inputted into this GlowScript formula to then output the distance here at 45 degrees, which is found on the left side. And then you can also see a visual horizontal axis and vertical axis here in the model. All right, next up are assumptions and / possible sources of error. Two assumptions that we found were as distance increases, the magnetic field begins to fall. So that's one assumption that we found from the experiment. And then the second assumption is that the bar magnet serves as a magnetic dipole. And we were able to see this through the experimentation as well. Some sources of error that could be found, which could have possibly skewed the results, was the location of the magnetometer, which it could not be precise, and then as well as outside environment, such as just electrical things that could affect the magnets, which could possibly skew the recordings. Next are observations. So two observations that basically just support the Biot-Savart law are when the magnetometer is far away from the magnet, it measures a near zero magnetic field in the x direction, and as it moves closer to the magnet, the measured x component of the magnetic field increases. And lastly are what ifs. So first is what if we redid the experiment, but instead of using a single magnet, we use two identical magnets stuck together end to end, how would you expect your measurements to differ? So the answer to this is that this would result in the direction of the field staying the same. However, it would cause the magnitude to double. So everything would stay the same, but magnitude doubles. And then our second what if is if you haven't oriented your setup so as to compensate for magnetic north and had instead laid out your meter stick at some intermediate angle with respect to Earth's magnetic field, how would your results have changed? And so what this would do to the essential results is that it would be affected as the Earth's magnetic field would with the bar magnets. The Earth's magnetic field would basically decrease the bar affect the bar magnet's magnetic field, and so therefore decrease in effect on the magnetic field. And that is all for lab 2. Thank you for joining.